A great deal of what we're going to be doing for the rest of our study of fluids depends on an understanding of fluids that we call the kinetic model or the kinetic theory of matter. This idea at its core is actually very simple. It just says that all objects are made up, or all matter is made up of little tiny particles, atoms, molecules, that's what we're talking about here, and that those are constantly in motion. And this is probably an idea that's not new to you. You have some background with this before, but the implications for it may be a little bit more novel. And so we'll continue with this for quite a while and explain some everyday phenomena with liquids and gases in particular, but really with all matter. We can learn some things from this way of looking at the universe. So the basic idea is that everything's made of little tiny particles, but we have a few assumptions that we make for calculation purposes, primarily just to make things a little bit simpler or less math heavy for these calculations. So first off, we assume that matter is made of a very large number of small particles, lots and lots and lots of atoms and molecules in any object that we would deal with, any macroscopic object. That's going to be a good assumption. We probably wouldn't apply this same model, or not the same way, if we're only dealing with a few atoms drifting around. We'd have to make some modifications, or it'd be a different situation. But that's not going to be something we typically deal with anyway, so that's fine. The separation between particles is the focus of the next assumption. We'll do a lot with the kinetic model involving gases. And so in between particles we have just empty space. And you might think, oh, okay, so it's just air in between particles. No, it's not air in there. It's totally emptiness. And there's nothing there. When I say we're between atoms, well, I mean, air is made up of atoms and molecules, and so we're between those even. So there's just emptiness. And basically we're going to treat these atoms and molecules as though they were little balls that are moving around. And so in gases, there's going to be a really big amount of space in between the little balls that are bouncing around. So relatively very small volume is taken up by the matter itself, by the atoms, and most of that volume is empty space. And then those particles in the gas, they move very, very quickly. They don't stick together really at all. We say that there's no interaction between these particles except when they collide directly. So when we have molecules that are moving less rapidly, they may stick together and form little groups, but that's not going to happen with gases. It will happen with liquids and with solids, though. With liquids, those attractive forces that tend to make them form little groups, they're going to be strong enough to hold things together into groups, though not real solidly. So we still have a lot of energy, a lot of motion in liquids, and so these substances, the atoms, they all pretty much stay together, but they don't maintain a constant shape. There isn't a big enough force to hold everything in a certain position. That's solid, where we have very large forces, just not much motion in the atoms. They just kind of wiggle around in place, but these forces are so strong that they keep the atoms arranged a certain way. And so those distances between particles are going to be the smallest for solids, a little larger for liquids, and the largest for gases, and that's going to influence, or that's an artifact of the interactions between molecules or between particles, which relates to how fast these particles are moving. We also need to understand that these things are constantly moving, always moving, never stopping. So we think of something like a tennis ball, and we can throw a tennis ball, and we can watch it bounce around, or a racquetball, watch it bounce around inside the court, off all the walls and the corners, and it moves for quite a while, but eventually it comes to a stop. Well, that doesn't happen with the atoms, with the small particles we're talking about here. They're always moving, and it turns out that the faster they move, the warmer that object will feel to us. Temperature and heat are just artifacts of motion, of kinetic energy at the atomic level or at the molecular level. So the faster these things move, the warmer that object is going to feel to us. So the inverse would be true here as well. The warmer an object is, the faster its particles move. And so if we go back to our solids, liquids, gases, if we have some solid and we start heating it up, gradually those particles are going to move faster and faster until these attractive forces are not strong enough to confine the atoms to a specific shape. They start to kind of move freely around each other. They still hold together basically, but this faster motion makes it so they can change their shape. They become liquids. And if we add even more heat to this, more kinetic energy for those particles, they move even faster. So fast, in fact, that these attractive forces, they're not big enough to hold these into groups at all anymore. And so we get our liquid change into a gas. These groups break up, and then particles start bouncing all around the place without any interaction with other particles. And then the last idea here is that whenever we have a collision between two particles, we're going to have a transfer of energy. And specifically, we'll assume that these are perfectly elastic collisions. And so that transfer of energy we're talking about is a transfer only of kinetic energy. Now that's really more of an approximation than a rule here. We know that in reality we are going to have some kinetic energy that changes forms. So these particles are made up of smaller pieces, protons and neutrons and electrons. And protons and electrons, they're both charged particles. And we'll talk later on in electromagnetism about how when you accelerate a charged particle, it radiates photons. It lets loose light, basically, electromagnetic radiation. And so that's energy that's in a form, not kinetic energy. And so actually we do have a little bit of energy that's sort of leaking out of our system in the form of photons, but it's going to be such a small amount that we'll just make the assumption that the collisions are perfectly elastic. And again, this is mainly to simplify our math later on.